Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the 23rd lecture of VLSI Interconnects course. We are in the third module of this course and currently we are discussing power dissipation issues in interconnects. In the previous lecture, we discussed different contributions to the total power dissipation. We saw that there is this dynamic power and short circuit power which contributes to the transient power dissipation, and both these powers are affected by interconnect. We discussed in detail about dynamic power dissipation, and we saw that dynamic power dissipation would scale linearly with interconnect width. In this lecture, we will continue with our discussion on power dissipation. More specifically, we will look at the dependence of short circuit power on interconnect width, and we will see how there is an optimum interconnect width which minimizes the total power dissipation. So, in the previous lecture, we were discussing about different contributions to the power dissipation, and we saw that there are these dynamic power and short circuit power dissipation, and this both these are dependent on the interconnect. So, your interconnect would affect both these. Then we also saw what is dynamic power dissipation, and we saw that dynamic power dissipation would scale linearly with width. So, if this is my interconnect width like this, so my P d would be there would be some constant, but it would increase. So, if I were to look at only the dynamic power dissipation, this analysis would tell me that my interconnect width should be minimum. So, to minimize P d, we would like to reduce the interconnect with W. However, we also saw that there is an additional power dissipation, the second one, which was the short circuit power, and then we discussed how short circuit power would be given by this expression approximately. Even in more complex devices, we saw that the short circuit power would be proportional to the transition time. So, we saw a reference where it was stated that irrespective of your load device characteristics or the far end device characteristics on your interconnect, your short circuit power would be proportional to the transition time. So, then we started with some qualitative understanding based on two pole equivalent Elmore model. So, we saw that if we take an unloaded case, so for unloaded interconnect, your B 1 would be equal to this. So, B 1 is essentially this is R C L square divided by 2, and your B 2, which is essentially L C L square by 2, would be given by this. So, here this we had seen that this B 1 is independent of interconnect width. However, B 2 depends on the interconnect width. So, your B 2 is actually linearly proportional to width. So, what we have is the following. So, your short circuit power depends on the switching time or the transition time. This switching time would be proportional to delay. Now, the question before us is how does the transition time depend on the interconnect width. So, for that we are taking equivalent Elmore model where I have an eta 1 like this. So eta 1 we have seen in previous lectures in module 2 that eta 1 is 1 by 2 into b1 divided by root over b2, where b1 and b2 are given here, we discussed above. And if I substitute the values of b1 and b2, I will get my eta to be something like this. So, now if I look at this eta 1 is inversely proportional to the root of w. So, after all simplification, I will get my eta 1 as something like this. So, the nature of eta will definitely depend on this k1. K1 is some constant. So, we are not varying the length L square, or we are not varying the inductance D and other things. If we keep all other parameters fixed, we just want to understand how would this eta 1 depend on W. So, we can replace all other things by some constant. So, we get a proportionality equation of this form. Now, let us investigate how this will translate to the effect on my delay. So, if I go back to the two pole approximation, we had something like this, right. So, we had these are three different values of eta. So, for when you have eta 1, let me call this with superscript 1 in this parenthesis. So, for this case you will have a response like this. For this case you have an eta 1 of 2, and for this case you have an eta 3 of 1. Now, from our previous analysis we knew that, I mean, this is an underdamped system, there are overshoots present with ripples. So, you would have this as less than 1, whereas this eta 1 of 2 superscript 2 would be greater than or equal to 1, depending on like whether this is just critically damped or over damped. And then what we can also say is that this would be greater than your eta 1 of 2. From this graph we can also see that your delay time TD1, TD2, TD3 is also sort of proportional to your eta 1. So, if your eta 1 is more, your TD1 is also more, right. So, so your TD1 is more than TD2, which is more than TD3. So, if you have an underdamped system with overshoots like this, your response time would be or your delay would be the least. Now, we are interested in the response time, which is actually would be proportional to this also, right. So, if I look at the distance between these two, so if from here to here, if I want to call this my response time, this would be proportional to delay. So, what we can safely say that my TR is proportional to, or let me write proportionality is proportional to TD. So, if I get an idea about TD, I can also get an idea about my transition time or the rise time, right. So, let us try to see like how this would be impacting the delay in terms of width. So, what we had was the following, that my eta 1 of 1 was greater than eta 1 of 2, which was greater than, or let me start with this time. So, my TD1 is greater than TD2, which is greater than TD3, and so from here I also have my eta. I also have my eta 1 greater than eta 2 of 1, which is greater than eta eta 1 of 2 greater than eta 1 of 3. Now, what we have is eta 1 is equal to some constant into W, right. So, there is an inverse proportionality here. So, from here if I were to write this for different values of width, I can then get that my W1 should be smaller than my W2, which should be smaller than my W3. So, now if I want to plot it, I would be getting something like this. So, if this one was my W1 and this is suppose my W2 and this is my W3. So, this is W1, W2 and this is W3. My TD1 would be greater, right. So, my TD1 which is like in blue here. So, my TD1 would be like this, then my TD2 would be somewhere here and then TD3 would be somewhere here. So, my delay would be decreasing with my width, right. So, basically your TD. So, this will not be a linear or so it will not be direct dependence like this. This graph is only qualitative. Let me clarify that we are only looking at the trend. So, I am not saying this is following exactly this curve. It is not a straight line like this, that we know. So, it is not like a straight line falling like this, but there would be a complicated function for TD depending on W1. But what we can say for certain is that for an unloaded interconnect, if I go on increasing my width, my delay time would reduce, or if I go on reducing my width, in that case my delay would increase. Now, how would this translate to the power dissipation? So, let us look at that, right. So, overall what will be the effect? So, let us summarize the effect of width on different parameters. So, my width is W. So, my resistance varies inversely with my width, right. So, if I increase my width, my resistance, I will have more cross sectional area. So, my resistance will go down. So, in that case my graph would be something like this. If I look at my capacitance is directly proportional to width. If I increase the width, I will have more area to store the charge, and therefore, my capacitance will go up. So, my capacitance would go up linearly like this, right. Now, what about the coefficients B1 and B2? So, as we have seen, your B1 will remain constant. So, this is B1 is independent of your width, while B2 would increase. So, B2 we had seen the dependence here. Let us confirm that. So, your B2 was linearly proportional to W. So, you would have a curve like this, right. So, this will be your B2 shown by red. So, this is your B2, right, and this blue curve is B1. Now, from B1 and B2, I mean we saw that your eta would be exponentially decaying with width. So, we had an expression of eta 1, this is 1 to be 1 by root over W. So, it will be reducing like this. There would be certain point here where this would be equal to 1. So, if I then look at this region, here your eta is more than 1. So, this would be this we can say is like an over damped thing. Right, and in this region your eta is less than 1. So, this would be your under damped. Right. So, we have this eta, and then we have also got an estimate about the delay. So, your delay would also be diminishing like this. Right. So, again these are also all qualitative plots only telling us what would be the trend on the delay. So, this is your delay, and this is your transition time. So, transition time would be proportional to delay. More is the delay, more would be the transition time, and therefore, we can say that your transition time would also reduce like this. Now, if we recall how was your power short circuit power dependent on your rise time. So, your P short circuit was proportional to your T rise. So, what this tells you is the narrower is your interconnect width, more is your rise time, and more should be your short circuit power dissipation. This is in an RLC interconnect and inductive interconnects. So, if we then look at the delay, basically your delay would be dependent on eta. So, this is a paper which we had referred to in earlier lecture also. This was on equivalent Elmore thing. So, from here, so this is your this is eta 1, in this also this is your eta 1, right. So, there is a sort of closed form expression, and you can get the get the delay from this eta 1, an approximate value. What this would finally tells us is that there is a conflict between the dynamic power and short circuit power. As we had seen in the dynamic power, if I reduce my width, my dynamic power was reducing. However, in short circuit power, if my rise time or the transition time increases, my short circuit power increases. So, if I combine this rise time with omega and get a relationship here, I would be getting something like this. So, here we have seen that this is your dynamic power, and if this is your short circuit power. So, I mean your rise time is reducing if you increase the width, right. So, your short circuit power should reduce. So, this is and this green curve here is your total power. So, this is your total power. So, your total power will have a shape like this, and then there would be some optimum width which will give you minimum total power. So, if you increase the width a lot, then your dynamic power will increase. If you reduce the width a lot, then your short circuit power will increase. So, if you are in this regime, then your loss is dominated by the short circuit power. If you are in this regime, your loss is dominated by the dynamic power, right. But this was the case for an unloaded interconnect. In practice, we will have a load and a source, right, because where does short circuit power dissipation happens? It happens in the device at your load end. So, in practice, there would be a source with some driver resistance, and then there would be some load which will effectively we can say this there is CL here. So, this is your load capacitance as we have done. Now, for for an RLC interconnect with a source resistance and load capacitance, we have already seen in previous lectures what will be your B1 and B2. So, just based on that analysis, let us try to infer how this delay would change. So, here we can see a few things. So, here RD and CL is constant, right. So, this is constant. Similarly, R into C, we have seen from previous analysis that this is also constant. So, this is also constant. Both these are constant. So, if I want to constant means they are independent of the interconnect width. So, by constant, let me clarify, I mean that both these terms are independent of your interconnect width. So, if I want to replace this with a constant, I can say that my B1 is some constant here K1. K1 now represents these terms, plus there is this RD into CL. So, this term is there. So, RD into CL is there, and then RL into CL. Now, RD is constant, whereas C depends linearly on. So, C depends linearly on omega, and in this case your L into CL is constant, but your RD is proportional to 1 by omega. So, I can replace this by an expression of this form, where I can write B1 as K1 plus K2 omega plus K3 by omega. This K1, K2, K3 are some constants, just to get a qualitative idea of like how this function will behave as a function of omega. So, this is for B1. We will come to this and we will plot how this would look like. If I look at B2, B2 has these terms. So, there is this term of L into L, the capital L inductance into the length into CL. So, all these terms are independent of width. So, we had argued in the previous lecture by giving some reference that L is almost independent of width. So, this is a constant, and this depends on your this depends. So, L is constant. So, C would depend on your width. So, your dependence on your dependence on C is there. So, this is proportional to W. So, if I then write an expression for B2, my B2 would be something like this, and then your eta will be B1 divided by half of B1 divided by root over B2, and from eta you will you can get the rise time, delay, and the transition times, whatever times you are interested in, right. So, now let us look at how this would behave. So, if I look at this B1, so B1 is interesting. Earlier in the case of an unloaded case, your B1 was constant, right. So, where are these dependence coming from? There is this RD term. If RD is 0, you do not have this. If CL is not there, I mean it is open circuit. So, in that case also CL is 0, and in that case this term is also not there. So, earlier B1 was constant, but now you have this B1 dependence dependence of B1 on omega, and if I look at it, you can see this. So, if your omega is very small, in that case K3 by omega would be large number. So, if you go on reducing this omega, the inverse will go on increasing, and in some limit this will be the dominating term. This will be the dominating term. On the other end, if you go on increasing the width, K3 by omega K3 by W would become small, very small, and in that case your B1 would be predominantly governed by K2 into omega. So, if I look at the plot, my plot would come out to be something like this. In this region where you have this inverse dependence on your width. In that case, what is dominating? Your this is dominating, right? R is inversely dependent on width. So, your R into L. So, your R into L into CL is dominating, whereas, so this is the case when if you go on reducing the interconnect width, at some point the resistance becomes so large that the resistance into the interconnect resistance into the load capacitance starts dominating your V1. On the other end of your analysis, you can see that here in this region you go on increasing the width. So, in that case your capacitance increases, interconnect capacitance increases, and then the driver RD into CL then starts playing a dominant role, and then this is dominated by your RD into C into L, right. So, this will be your dependence. Now, your eta is anyways 1 by 2 B1 by root over B2. So, now I mean if you look at this in the low width regions, your B2 is reducing while your B1 is increasing. So, in that case your eta would increase further, and you would get finally delay would be something like this. So, again this is width, and your so this is again qualitative plots only. Right. So, your width delay would change like this, and similarly your rise time would also vary like this. Now, let me show you the computational plot from one of the references. In last lecture, we towards the starting we cited this reference. So, this figure I have taken from ABG Friedman's paper on power characteristics of inductive interconnects. We had cited this paper in the previous lecture. So, here you can see the interconnect width is in micrometers, and the transition time. So, transition time is going like this. So, we have argued that your transition time would look something like this. So, this is from computation. Here you can note that here the interconnect width is in the log scale. So, it is not a linear scale for the width. Now, if I look at the total power dissipation with source and load, again from this paper we can see it is from the same paper. There is this qualitative plot like one which we had argued, and here we can see that your short circuit power dissipation is slightly increasing after a certain point. So, it is not that it is for an unloaded case, for example, it was going down throughout, but it is not the case. I mean, when there is some load, it will also be there, right. So, here the total transition power would be something like this, and here there would be an optimum interconnect width. So, this would be your so, this is your optimum interconnect width. There is also a computational plot in the same paper. So, here you can see that this n is the number of logic gates which is at the far end of your interconnect. So, you have an interconnect like this, and then there are different number of logic gates. So, when you are increasing the number of logic gates, in that case you are increasing these CLs, right. So, you are changing that. So, here you can see that if you go on increasing the number of your logic gates which is driven by the interconnect, this transient power, total transient power is increasing, and one of the main reason is that when you do that, you, as we saw, your B1 is increasing, and so is your this thing. So this is the region where this was RL into CL. So if your CL goes on increasing, this will increase further for lower widths, and that will translate to characteristics like this. So as you increase the load, your transient power will increase, right. So in this lecture we have seen that the total transient power dissipation in interconnect does not vary linearly with interconnect width. So there is an optimum interconnect width which minimizes the total power dissipation. This discussion on power dissipation in this lecture and the previous lecture is not exhaustive at all. This should be taken as a starting point. So if you want to have further reading, one of the immediate topics that you can read is minimizing power dissipation with repeater placement. So in the mitigation of delay, we had seen that we can place these repeaters to reduce the delay. So to make so delay increases as a power of L square if we place the repeaters in between. We try to linearize the increase of your delay with length, but these repeaters will also consume some power, and your overall analysis should incorporate the power dissipation in this with repeater placement also. So that is an immediate topic that can be taken up for further reading. In the next lecture, we will start with heating and thermal effects. So as we have seen that there is power dissipation, where will this power go? It will translate to heating, and that will introduce more complications in your analysis. So that's all for today. We will meet in the next lecture. Good day.